Hey there, chemists. In this lesson, we're going to look at how we draw Lewis structures for small molecules and polyatomic ions. First, some rules. To build a structure, you sum the valence electrons in the formula. You use a pair of electrons to bond the atoms together. Typically, the less electronegative atom is in the middle, and H is never in the middle. You arrange the remaining electrons to satisfy the octet rule, so that each atom feels like it has 8 electrons, but only 2 for hydrogen. And if there's extra electrons, you put them on the central atom. You'll see all of these rules when we do some examples in a moment. Here's an example of a Lewis structure for the nitrate anion, that's NO3 negative. So how do we get this structure? Well, the valence of nitrogen is 5 because it's in group 15. The valence of oxygen is 6 because it's in group 16. And then there's a -1 overall. So my valence to work with is 5 plus 3 times 6 plus 1, which is 24 electrons. And if you count how many you have, you've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons total. And you'll notice the overall charge is put outside a pair of brackets right here. Now we'll also see an example where you don't use the brackets and instead you put what are called formal charges. And that is little symbols like this, a positive on the nitrogen and a negative on each oxygen. We get those by comparing how many valence electrons an atom has and comparing it with how many unshared electrons and shared electrons it's bringing to the table in a formula. So the formal charge is essentially what charge an atom would have if both the atoms equally contributed electrons when they bond. That's not how we get these structures, but that's what shows us who's more electron poor and who's more electron rich, and that tells us how things react. You can get the formal charge by subtracting how many bonds and dots from an atom's valence. So let's go up and look and see where these come from in the nitrate example. Well, the nitrogen has a valence of 5. It's making 1, 2, 3, 4 bonds, and it has no dots on it. So 5 minus 4 minus 0 is 1, hence the +1 formal charge. The oxygens that have charges, if you look at their valence, well, each oxygen has a valence of 6. It's making 1 bond, and they have 6 dots, so that's a -1. In fact, that's true for both oxygens. So we put a little negative near the symbol for oxygen. This oxygen at the top has a valence of 6, it's making 2 bonds and 4 dots, so there's no formal charge, and then you just leave it alone. You just write the symbol as is. You'll also notice that the sum of the formal charges equals the overall charge of the formula. That will always be true. And we're going to focus more on structures that do include formal charges as opposed to the bracket notation. They're both acceptable, but we're going to exclusively look at the ones with formal charges in this course. Okay. So let's get to it and draw some examples. The first thing to do is to count your valence. So in water, there's 2 hydrogens at 1 valence each, plus 6 for the oxygen, so that's 8 valence electrons. Oxygen will be in the middle, and each hydrogen will start by singly bonding to the oxygen. Now satisfy your octet everywhere. The hydrogens are good because they only satisfy the duet rule, but the oxygen needs 4 more electrons. 1, 2, 3, 4. I've used up exactly 2, 4, 6, 8 electrons. That's your structure. No double bonds needed, no charges. In HF, we have 1 valence for the hydrogen, 7 for the fluorine, so this is also 8 electrons. Here we only have 2 elements, so they must be bonded to each other. Hydrogen is good, it always just makes 1 bond. Fluorine, however, in this structure needs 6 more electrons in order to satisfy the octet. 2, 4, 6, 8. Remember, the bond counts as 2 electrons. Even though it's shared, it feels like the fluorine gets the advantage of that, so it feels like it has a noble gas configuration. That's why they bond in this fashion. And that's exactly 8 electrons, so that works as well. In carbon tetrafluoride, we have 4 for the carbon, and then there are 4 fluorines at 7 each. That's 32 electrons. The less electronegative carbon goes in the middle. I start with single bonds and then fill in my valence. There's 2, 4, 6 on each fluorine to satisfy the octet. Carbon's already good. He already has 2, 4, 6, 8 electrons. And if you check your count, that's 32 electrons. We've satisfied the octet. and we've satisfied our electron count, and that's what you want to do in all of these compounds. When we get to nitrogen, count your valence. That's 2 nitrogens at 5 electrons each. That's 10 electrons. If you start with a nitrogen-nitrogen single bond and then satisfy the octet everywhere, you'll find that you don't have enough electrons to do this. This is 2, 4, 6, 8, 10, 12, 14, which is not equal to 10. So what do? You need to share more. Need to share more. So how do we do that? Well, get rid of a lone pair on each of the nitrogens and make them share another single pair of electrons. There we go. And then that's still not few enough. We need to get rid of another pair from each one and have them share another bond. Now you're satisfying the octet on each nitrogen, 2, 4, 6, 8, and you've got exactly 10 electrons total. So when you don't have enough electrons to satisfy the octet everywhere with only single bonds, you just need to share more until you get it down to what your valence is. You can only use the valence. You can only use the valence. You can only use the valence. Okay, so hit pause and see if you can come up with the next 4 in this set. What would the structures look like for CO2, phosphine, ammonia, and methane? Try that now. Okay, let's see how you did. Carbon dioxide has 16 electrons. There'll be a central carbon. You should have found that you make 2 double bonded oxygens on either side with 2 lone pairs each. If you came up with a structure where there's a singly bonded oxygen and a triply bonded oxygen, that's actually what's called a resonance contributor of this. It does satisfy the octet and it does use 16 electrons, but it'll have formal charges on the 2 oxygens. And we try to minimize formal charges, so 2 double bonds is the preferred way to draw this. In the phosphine molecule, there's only 8 electrons. It's a central phosphorus with 3 singly bonded hydrogens and 1 lone pair on the phosphorus. No formal charges, no double bonds. Ammonia looks almost exactly the same. It's also 8 electrons. It's just a nitrogen in the middle instead of a phosphorus. Makes sense. Phosphorus and nitrogen are in the same column of the periodic table, so they bond very similarly to each other. And then the last one, methane, last one in the series, is also 8 valence electrons. You have a central carbon with 4 singly bonded hydrogens. There's actually no lone pairs and no double bonds in this structure. So those are just some classic examples that you should be able to draft pretty quickly without too much effort. And they all satisfy the octet, and none of them have formal charges. Now let's look at a few cases where you don't satisfy the octet. Where are we less than the octet or above the octet? The 2 most common examples where you have fewer than the octet are species with boron and beryllium. Boron has 3 valence electrons, and in this boron trichloride, there's 7 for each chlorine. So we have 24 electrons. And if you draft a structure with a boron in the middle and bond it to 3 chlorines with single bonds, go ahead and satisfy the octet on each chlorine atom, that actually uses up all your electrons. That is 24. So in this case, boron doesn't satisfy the octet. Doesn't satisfy octet. And that's as good as we can get it. Now what that does is it tells us how boron compounds behave. So when we react molecules that contain boron species like this, we know that they're very electron deficient because of that falling shy of the octet. So they'll react with things as a result of that. The other example right next to it is a beryllium compound. I know beryllium's a metal, but we see it form covalent looking species like in beryllium dichloride. This is 16 valence electrons, and it's a little linear molecule with a beryllium singly bonded to 2 chlorine atoms, and again, not satisfying the octet, just like boron, electron poor and reactive as a result. The 2 right next to that are examples that exceed the octet. Here's sulfur hexafluoride and chlorine trifluoride. If you count your valence for SF6, you get 48 electrons from the sulfur and 6 fluorines. That's a central sulfur with 6 singly bonded fluorine atoms, and each fluorine will have 3 unshared pairs of electrons. And that's a valid way of drawing SF6. Very symmetric molecule, but we are exceeding the octet. Many textbooks say that this can be done because sulfur has empty d electrons. Sulfur has empty d orbitals, although there's some evidence that suggests that this species exists as an ion pair. So if you see this later on in your chemistry career as an SF4 cation and 2 fluoride anions, don't be too afraid. This is also an acceptable way of showing this. I've actually seen evidence, some papers that write about this where they talk about it depends on what state the species is. If it's a solid or a liquid or a gas, it actually has slightly different bonding. We're going to draw it like this because it's symmetric, and a lot of textbooks still show it like this. But just be aware that chemists are actually still researching what these things really look like, and it's not 100% agreed upon just yet. There's still learning to happen. In the last example of this row, we've got chlorine trifluoride. That's a central chlorine atom with 3 singly bonded fluorines. Each fluorine has 6 unshared electrons on it. And if you count your valence, you've got 28 electrons to work with. If you put 1 pair on the chlorine, that satisfies the octet everywhere, but that's only 26 electrons. So what do we do when I don't even need all the valence? Here's a case where you put the extra electrons on the central atom. Extra electrons go on the central atom. And this is commonly seen for things that can exceed the octet, elements that have empty d orbitals, which is row 3 and below in the periodic table. If you go back to the periodic table, you can see that anybody in the 3rd row has d orbitals because d starts with 3d. It also occurs usually with atoms that are bonded to very greedy electronegative elements like fluorine or oxygen. So that central atom with the extra electron pair doesn't really feel like he has full ownership of all of those electrons because there are significant dipoles pointing toward the more electronegative peripheral atoms. Okay, so those are some exceptions to the octet. We'll wrap this lesson up by looking at a lot of examples that use both of those rules but also have formal charges. Now, formal charges, to reiterate what we said in the beginning, is the charge of an atom if both atoms equally contribute electrons in a bond. We get them by subtracting the unshared electrons and half of the shared electrons from whatever the valence of that element is. And I just memorize this. It's the valence of an element minus the bonds it's making minus the dots in that structure. Let's do a few examples, starting with a simple one, the NO plus cation. That's 10 electrons, 5 for the nitrogen, 6 for the oxygen, and 1 fewer because of the plus charge. That's how you get 10. There's only 2 elements, so it must be a nitrogen bonded to an oxygen, and this actually has the same electron count as N2. So if you look back up at the upper right, it's going to have the same bonding pattern. It's going to be a triple bond with a lone pair on each of the elements. Now, what about the formal charge? Well, nitrogen's valence is 5. Here it's making 3 bonds and has 2 dots. So this has no formal charge on the nitrogen. The oxygen, however, with a valence of 6, making 3 bonds and 2 dots, has a value of 1 for its formal charge. So you put a little plus with a circle around it and somewhere near the elemental symbol. The sum of the formal charge is equal to the overall charge. In this case, +1 is +1. Right next to it, we have ozone. Ozone has a total valence of 18 electrons. It's going to be an oxygen connected to a second oxygen connected to a third oxygen. And because of your electron count, you're going to need 1 extra shared pair of electrons, 1 double bond, either between the first 2 or the second 2. Those are equivalent. They're actually 2 different resonance contributors, equally contributing. We'll learn about those later in this unit. And then you need 6 unshared electrons on the singly bonded oxygen, 2 on the central, and then 4 on the outermost electron. Now, about formal charges, the formal charge of the oxygen on the left, that's a valence of 6 minus 1 bond minus 6 dots, so -1. The one in the middle valence of 6 minus 3 bonds minus 2 dots, that's 1. So there's a formal charge of -1 on the singly bonded oxygen and +1 on the middle oxygen. No formal charge on that oxygen. So overall charge is 0, but we have a more electron-rich oxygen and a more electron-poor oxygen, and this tells us how the molecule reacts. Next to that, the carbonate anion, that has a total of 24 electrons. That's a central carbon bonded to 3 oxygens. 2 of them will be singly bonded with 3 lone pairs. The other one has to be doubly bonded in order to satisfy the octet and use up exactly 24 electrons. Formal charges, you'll have a negative on each of the singly bonded oxygens, and the other elements have no formal charge. The nitrous oxide molecule, N2O, that has a valence of 16 electrons. That's a nitrogen connected to a nitrogen connected to an oxygen. And there's actually a couple of ways you could do this that are acceptable. You could put 2 double bonds, have 4 electrons on the left nitrogen, 4 dots on the oxygen, and then if you count your formal charge, the nitrogen on the left, that's a valence of 5 minus 2 bonds minus 4 dots. That's actually a negative formal charge on the nitrogen. The middle nitrogen has a valence of 5 minus 4 bonds minus 0 dots, so that means the middle nitrogen has a +1 formal charge. Oxygen is 0 formal charge in this case, but this actually isn't the only way to draw this. You could show another version of this that looks just as good, except you could have an NN triple bond and an NO single bond. That would result in 1 lone pair on the left and 3 lone pairs on the oxygen on the right, and it changes the placement of your formal charges. The middle nitrogen is still positive, but now the oxygen on the right is negatively charged instead of the nitrogen on the left. So which of these are true? Well, both are correct. This is a sneak preview into what's called resonance contributors. And we'll even give a head start on which one is better. It turns out the lower one is preferred because the negative is on the more electronegative oxygen. So when we have a competition, you want the negative charge to be on a more electronegative atom, whenever that's the case. Okay, so lastly, I want you to hit pause one more time and see if you can figure out the final row of examples in these examples with formal charges. All of them actually do have formal charges, and see what you come up with. Okay, let's see how you did. So the carbon monoxide molecule has 10 valence electrons. That's a CO triple bond. There's a lone pair on each one, and the oxygen will have a formal charge of plus. The carbon will have a formal charge of minus. So there are 2 charges, but overall it's net neutral. The sulfate anion, SO42-, that has 32 electrons, and this actually will exceed the octet. To minimize formal charges, you'll have 2 doubly bonded oxygens, 2 singly bonded oxygens, and then various lone pairs all over the place to satisfy the octet on the oxygens. Sulfur is exceeding the octet, but it can do that. It's in the 3rd row of the periodic table. And then we have formal charges, in this case a negative on each of the singly bonded oxygens. If you drew a structure that has all singly bonded oxygens, it's not wrong. You just have more formal charges. As a result, you would have a 2+ on the sulfur and a negative on every oxygen. Structures that minimize formal charges are preferred. Let's write that. Structures which minimize formal charges are preferred. The ammonium ion is a little simpler. There's only 8 electrons, and that's going to be a nitrogen with 4 singly bonded H's. There's going to be a plus on the nitrogen. And then lastly, the phosphate anion, that has 32 electrons, and it's actually going to look very similar to the sulfate, but there's only 1 doubly bonded oxygen and 3 singly bonded oxygens with lone pairs on all those oxygens to satisfy the octet. We're exceeding the octet on phosphorus. That's okay. Phosphorus is in the 3rd row. And our formal charges, you have a -1 on each of the singly bonded oxygens. Again, if you made this with 4 single bonded oxygens, you're not wrong. You just have more formal charges, so it's a less significant contributor than the one that we have here. Okay, so that's how we draw structures of compounds using their valence electrons, satisfying the octet, and writing correct formal charges. Thanks for watching.